We have just wrapped up looking at linear functions, and now we're going to transition into absolute value functions. So I have absolute value functions. We're also going to do a bit of like a review on function notation, evaluating functions, and then graphing absolute value functions, and later on down the line we'll shift into solving absolute value equations and inequalities. However, I did want to introduce you all to like standard form of an absolute value function and kind of show you what each part of the function does. So standard form of an absolute value function is a absolute value of b, open parentheses, x minus h plus k. And I'm going to take each one of these pieces and kind of divide it up into what it does to the parent function, which in this case f of x, or you can say y equals absolute value of x. This is your parent function. So anytime we make any changes to the parent function, it will be as a result of changing any of these variables, and it'll produce a different graph, like a different shape. It'll behave differently. So if we look first at a, if it's greater than 0, meaning and it is less than 1, then it is going to be a vertical compression. So we'll get into some examples and what this all looks like in a little bit. Also, if a is greater than 1, it is going to be a vertical stretch. Sorry, my handwriting's a little bit off right now. So we got, if a is greater than 1, it's a vertical stretch. If it is greater than 0 but less than 1, is a vertical compression. And if we have a negative in the front, so if this a is less than 0, meaning it is a negative in the front, it flips the graph across the x-axis. Alright? So now we'll move on to our next variable, which is b. I'm going to try and do these in different colors so you all can see the difference. So if we look at b, if b is greater than 1, and I like to think of anything that falls like inside the absolute value symbol is going to do the opposite of what we think it should do. Because when I think about plus or positive, I'm thinking about going to the right in a coordinate grid, and I'm thinking about going up on a coordinate grid. But inside the absolute value symbol is a little bit different. So if b is greater than 1, it is going to be a horizontal compression, which is counterintuitive. It's actually going to compress the graph instead of stretching it. If b is greater than 0 but less than 1, then it is going to be a horizontal stretch. So if b is a fraction between 0 and 1, and then finally if b is less than 0, meaning it is a negative number, it is a reflection across the y-axis. However, you won't really see this one as much because the absolute value function is symmetrical, so sometimes those flips don't exactly matter as much. So if we go to our next variable is x, that's just our input. So for sake of simplicity, this is just, I'm going to leave it as input, or your domain. That's the values that we're going to put in, and I'm going to move more so to your h value. So h, so it'll be minus h by default, and then absolute value. So if your h is a minus h, then it's actually going to move to the right based on the number for h. So if h is 2, and it's minus 2, it'll move 2 to the right. If h is plus, then it's going to actually move to the left based on that number. So if it's plus 2, then it's going to move to the left 2. And then finally we have k. So k is, if it's plus k, so if it is plus k, then it's going to move it up based on the number that you're adding or subtracting. And if it's minus k, it's going to move it down based on the number that you're adding or subtracting. Okay? It's really important that you keep in mind the separation between b and then open parentheses and x minus h. The reason why is because in some examples you can factor out the b and then multiply it times a to be able to figure out how to easily graph your function, or you can just use the b or the a, whichever one, to easily graph your function, as opposed to if it's all connected. So give an example. If it looked like this, so I got absolute value of 3x plus 2, you would think initially that that plus 2 would move your entire graph to the left 2. However, that is not the case. In all actuality, this should be written like we have it up here with parentheses. So I'm going to need to take out the 3. So this will be absolute value of 3x plus 2 over 3, which means that my graph actually moves to the left 2/3 as opposed to moving to the left 2. And we'll get into some examples of what that looks like as well. So if we go into kind of defining function notation, so if I gave you a function and I said f of x is equal to 2x plus 3, each part of this function serves a different purpose. So the letter out front is just the name of the function. The letter out front is just the name of the function. The letter in the middle, your x, is your input value or your domain, and then all of the rest of this stuff is your output or your range. So what you're basically saying is, if you plug in an input value for x, you would get out f of x, or just to kind of refresh your memory, f open parentheses x means f of x, which means the value of f, meaning the name of the function, for the input value of x. Alright? And function notation can be a little tricky, but it's basically just basically the way a function is written. And it was originally intended to kind of simplify things. So if we had like an absolute value function, you wouldn't have to write absolute value every single time. Absolute value of whatever your function is every single time. You could just say like f of whatever the function is, and then it also helps you to create new functions from your original function that you're using. And again, we'll get into examples of that in a little bit. Your domain, again, your domain is going to be your x values, also known as your inputs. So you have to put something in to get something out, and then your output is going to be your y values. And in this particular case, it'll tell you not only the output / the range, it just tells you what a function does. Alright? And then the vertical line test, it basically says if you draw a vertical line through, and in this particular case I'm going to say a relation, because all functions are relations, but not all relations are functions. If you draw a vertical line through a relation, and you touch more than one point, in that relation, then it is not a function. You have to have each input has to have one unique output. Which is your y. So each input, which is your x, has to have one unique output, which is your y. So give an example. X can't be equal to a positive 2. So let's say x is 1. It can be equal to both a positive 2 and a positive 3. You have to have one specific value for each x. Now you can repeat your y values, but you cannot repeat your x values. So whenever we're looking at function notation and we're trying to evaluate functions, again, we look at the x values. It's just the input for our function. So in this particular case, it's telling us f of 2 is equal to something. And all we're essentially doing is plugging in for our input value of 2. That should be a 7. I'm sorry. So 3 times 2 is 6 minus 7. So f of 2 is equal to 6 minus 7. And so f of 2 is equal to a negative 1. And again, this is our x value, and this is our output, which is our y value, and it gives us an ordered pair of 2 comma negative 1, which is actually a point on this function f of x. So wherever I put in a 2 for x, I get a negative 1 for y. And so if we were to plug these back in, we should get a balanced equation, and that'll tell us whether or not we got the right values. So if we plug in negative 3, so this will be 3 times a negative 3 minus 7. So f of a negative 3 is equal to a negative 9 minus 7. So that means that f of a negative 3 is equal to negative 9 minus 7, which is a negative 16. So negative 3 comma negative 16 will be our value for the function. So if I put in an x of a negative 3, I get an output or a range of a negative 16. We'll look at a little bit more complicated example, but still the same principle. So you got this negative 2. The negative 2 goes into your input. So I've got 3 minus 1/2 times a negative 2. So h of a negative 2 is equal to 3 minus negative 1/2 times a negative 2 is going to be a positive 1. Because when you multiply in fractions, this is the same thing as saying negative 2 over 1. You multiply straight across, and that would simplify as a negative 2 divided by a negative 2, which is just plus 1. So that means that h of a negative 2 is equal to 4. So I got a negative 2 comma 4. And this is going to be my x value again, and this is going to be my y. And then I have one more example where we have h of 4 is equal to 3 minus 1/2, and then you plug in a 4 for your x value. So h of 4 is equal to 3 minus 1/2 times 4 is 2. It means that h of 4 is equal to 1. So this will be your x value of 4, which is your input, gives you an output of 1. So whenever you're trying to evaluate a function and they give you a number in parentheses, they're basically telling you that you're going to plug in that value for 4. So if we look specifically at the parent function for absolute value, we're going to go ahead and graph it and create a table for our absolute value function. So I like to do x and y, and I choose a few values lower than x, and a few lower than 0, and a few values above 0. And if you look down here at the bottom, we actually have the general form, because we're going to do some transformations of our parent function of absolute value of x. So if I take my value of x and plug it in, absolute value of a negative 2 is 2. And now some of y'all may be wondering, what does that even mean? So when I think about absolute value, I think about distance from 0. Excuse me. Distance from 0. So if I have 0 right here on the number line, and I go back 1, 2, negative 2, I'll go a total of 2 numbers, 2 steps to get to a negative 2. And then even if I went to a positive 2, so 1, 2, I want a total of 2 steps to get to a positive 2. And the way I think about it is distance. Distance from 0, I'm not sure if you all have ever heard of it, but I haven't heard of a negative distance. Even if you walk backwards, you're not walking a negative distance. So if you catch a bus somewhere, or you ride a car, or drive a car somewhere, and you go back the exact same way that you came, you're still going 2 different distances, and both of them would not be seen as negative. You're traveling a positive distance. So if we look at negative 1, absolute value of a negative 1 is 1. Absolute value of 0 is just 0. And here is where some of y'all may get tripped up. Absolute value of 1, it doesn't flip the sign of positives. Positives stay as a absolute value. It stays a positive, so it'll be positive 1. So absolute value of 2 is just 2. And now that we have some points, we can graph our parent function. So if I go negative 2 and then I go up 2, I got a point right here. If I go negative 1 and up 1, I have a point right here. If I go to 0, 0, 1 and 1, 0, 0, and I can see a pattern. So this way is going up by 1, so I can kind of keep that going. And this way I have a pattern. I see it going up by 1. I can keep that going. And then get a straight edge, and I can graph my function. So a few key things that I want to point out about this function is the vertex, the domain, and the range. So when I think about the vertex, I think about where it changes direction. And so in this particular case, it'll be the lowest or the highest point. So I'll just put that off to the side. It's going to be the lowest or highest point. And it'll be the change of direction slash change of direction. So if you look at your absolute value symbol graph, it looks like a V. And so right here would be our vertex, which in this case is 0, 0. And our domain, which is also our x values, if you look at this graph, it's never going to stop going from left into right. So our domain is going to be all real numbers, or a negative infinity to a positive infinity. However, when you're looking at the parent function, the range is where you may end up with some restrictions on what your range values can be based on your input or your x values. We don't actually call them restrictions, but your range is limited based on the absolute value function. And then the parent function, if you look, the lowest point for your range is a 0, and then it never stops going up, so it'll be to a positive infinity. The bracket means equal to, so that's why the 0 is in the equal to symbol. So if we go through a few more examples, and this will kind of introduce us to transformations as a whole. Alright, and so if we look at this first example, and we think about what we did on that first slide with the transformations to your absolute value functions. Here, the only thing I'm doing is adding 4 at the end, and it's outside of my absolute value symbol. So if I know my transformations right off the bat, I know that this is going to move my entire graph up 4. And when I say it'll move my entire graph up 4, the very first thing that we graph, anytime we have a parent function, would be, or an absolute value function, would be to graph the vertex. And in this particular case, the parent function vertex is at 0, 0. So if they move it up 4, it'll go up 1, 2, 3, 4, and I have a point right here. So my vertex is 0, 4 because I moved my graph up 4. So I'm going to create a table so I can actually evaluate my function. So I've got x and I've got my y, and in the middle I've got absolute value of x plus 4. And again, I'm going to choose some values below and above 0. So if I plug these in, I got a -2, absolute value of a -2 plus 4. The absolute value of a negative, it just changes the sign to a positive. Sorry, I didn't realize you couldn't see that. So absolute value of a -2 is a +2 plus 4 is 6. And then absolute value of a -1 is a +1 plus 4 is 5. Absolute value of 0 plus 4 is 4. Absolute value of 1 is just 1 plus 4 is 5. And then absolute value of 2 is just 2 plus 4 is 6. And as you can see, this right here is my vertex. As I go to the right of my vertex, I'm going up by 1 as my x values go up by 1, and as I go to the left of my vertex, my y values are also going up by 1 as my x values go down by 1. So if this were a linear function, it would just continue going straight like this, but instead, since it's an absolute value function, it creates a V. So if I graph these points, make sure I'm not messing up the rest of my papers. So if I graph these points, I already have my vertex at 0, 0. At -2, my y is a -6. At -1, my y is 5. +1, my y is 5. And at +2, my y is 6. And you can see the pattern that is going up by 1 and to the left by 1. Very similar to a slope of a line. However, we can't exactly call it a slope because we're dealing with a different type of function. So if I continue going here with my straight edge, I can see that my entire graph is shifted up by 4. So the first question I'm going to ask myself is, what is a domain? With absolute value functions, the domain usually isn't going to change, and in this case it didn't. It's going to keep going from left to right forever and ever and ever. So this will be a negative infinity to positive infinity, or all real numbers. However, because I moved my graph up right here by 4, that's going to change my range. Now, instead of it being 0, 0, which is what my parent function was, it's going to be the lowest number of 4 to a positive infinity. So my lowest y value now is 4, taken straight from my vertex, and then goes up to infinity from there. Let's look at another example. So here, I've got an x -2 on the inside. So this -2 is actually going to be my h. And if we think about the transformations, that -2 is actually going to move my graph to the right 2. Which means that my vertex is now going to be 2, 0. Because if you move it to the left or right, it affects your x values. So I know that my vertex now is here. So let's go ahead and evaluate the equation, the function. So I've got x, I've got y. I'm going to pick some values below and above 0. I'm actually going to go a little bit lower on these just because I know that my graph is shifted to the right. And in the middle I have absolute value of x -2. So I have absolute value of a negative 2 minus 2. Negative 2 minus 2 is a negative 4. Absolute value of a negative 4 is a positive 4. So if I go to the negative 2 side, go up to a positive 4. Absolute value of a negative 1 minus 2. Negative 1 minus 2 is a negative 3. Absolute value of a negative 3 is a positive 3. So my next point is at negative 1, positive 3. If I go to 0, which is the where my vertex is located for my parent function, this would have been 0, but instead I have absolute value of 0 minus 2, which is a negative 2. The absolute value of a negative 2 is a positive 2. And then absolute value of 1 minus 2 is a negative 1. Absolute value of a negative 1 is a positive 1. And then if I go to the right one, go up 1. And then if I have absolute value of 2 minus 2, 2 minus 2 is 0. So absolute value of 0 is 0. And then I have absolute value of 3 minus 2, which is 1. And the absolute value of 1 is just 1. And then the last one is 4 minus 2, which is the absolute value of 2, which is just 2. So I got a dot right here and a dot right here, and it just keeps going. And then again, if I take my straight edge, I can actually graph my function. Graph my function and easily see that all we did was just shift the vertex to the right 2. And with that being said, our domain would remain the same, still all real numbers, or negative infinity to positive infinity, and then our range would actually be the same as well, because we didn't move our graph up or down, so it'll be a 0 with brackets to positive infinity. Now if we look at this third example, example C, I've got a negative in the front, and that applies to my A. We actually kind of treat the A and then the negatives in the front independent of one another, which means that it's going to flip my entire graph across the x-axis, which means that my vertex would actually stay the same, 0, 0, because I didn't move my graph up or down or left or right. And my domain is still going to be negative infinity to positive infinity. However, now that my graph has been flipped, my range is going to be from 0, to a negative infinity. And I'll show you what that looks like here in just a minute. So I'm going to go ahead and put a dot for my vertex, which is at 0, 0. And let's go ahead and evaluate the function. So I got my x values, I got my y values, negative 2, negative 1, 0, 1, and 2. And it's going to be negative absolute value of x equals y. This is a negative absolute value of a negative 2. Absolute value of a negative 2 is a positive 2. And then you multiply that times a negative, and you get a negative 2 for your y. So if x is a negative 2, my y is a negative 2. If I got a negative absolute value of a negative 1, this would be a negative 1. Negative absolute value of 0 just stays as a 0. And then negative absolute value of 1 would be another negative 1, because absolute value is 1 times a negative is a negative 1. And then the negative absolute value of 2 is a negative 2. So if I graph my function, it looks like this. And I notice the pattern is going to keep going when I'm graphing. And then we take our straight edge. I'm going to make it nice and pretty. Mine is not nice and pretty, but you guys get the idea. And if we look back at our range, the reason why it was 0 to negative infinity is because now this becomes one of the highest points, which would be like a maximum in this case, and the highest value for y is 0, and then it opens up down, which means that it goes to negative infinity. And then this last example here, it got a 2 in the a's place, which means that it's going to be a vertical stretch by 2. So if we evaluate this function, I have my x's, 2 absolute value of x, and then I get my y's, and again I'm going to choose some values above and below, negative 2, negative 1, 0, 1, and 2. I generally like to use at least 5 points to graph a function. So going back over here, I got my vertex. That never changed because I didn't move my graph up or down. And then my domain, again, it's going to stay the same. And my range is actually going to stay the same, which is bracket 0 to positive infinity, because I didn't flip it, I didn't move it up or down or anything like that. So I've got 2 times the absolute value of a negative 2. Absolute value of a negative 2 is 2 times 2 is 4. So if my x is a negative 2, my y is 4. I got 2 times the absolute value of a negative 1. Absolute value of a negative 1 is a positive 1 times 2 is 2. So if it's a negative 1, it goes up to 2. And then 2 times the absolute value of 0 is just 0, because anything times 0 is 0, and the absolute value of 0 is 0. And then 2 times the absolute value of 1. Again, this is where my pattern starts to change. It's to change the direction, because this was my vertex right here. So now it is 2, and then I can predict again that 2 times the absolute value of 2 is just going to be 4. So if I go to the right 1 and go up 2, go to the right 2 and go up 4, and we look at our function, it is a vertical stretch, which means that our graph is more narrow. The reason why is because our y values are actually going up at a faster rate than our x values. So one way that you can think about this when graphing, as opposed to plotting all of these points, is if you get your vertex right, you're going up 2 and to the right 1, which is the same as a. Up 2 to the right 1, and then up 2 to the right 1, up 2 to the right 1, up 2 to the right 1, up 2 to the left 1, up 2 to the left 1, up 2 and to the left 1. And then if we look at these last few examples, again, this is A and this is K. So it's a negative, which means that it is reflected across the x-axis, and it's shifted down 23, because K moves my graph up or down. And when I say shifted up or down, I'm talking about the vertex. So that means that this vertex is going to be 0, negative 23. And since it's flipped, it's going to change my range to a negative 23 to negative infinity. Sorry if I ran out of space. I just decided to kind of add that one in there. Looking at B, this is my H and this is a K. So it is shifted. Again, if it's inside the absolute value symbol, it does the opposite of what we think it does. So since it's minus H, it's actually going to go to the right 14, your vertex, that is, and then it's going to go up 17, which means that my new vertex is 14, 17, and it's not flipped or anything. My domain will stay the same, but my range is going to be bracket 17 to infinity. And then if we look at example C, this negative in the front applies to my A. The 3 is my A, and this is a K. So the negative in the front reflects it. Move it up a little bit. Across the x-axis. The a of 3, meaning that it's greater than 1, is a vertical stretch by 3, and when I say by 3, that is a factor of 3, and then it's going to go up 42. The vertex is going to move up 42, so my new vertex is 0, 42 for the vertex, and then my range will change now that we changed the y value, and it'll be bracket 42, negative infinity, because since it was flipped across the x-axis, my graph is opening down, which means that my y values are going to continue to get smaller and smaller and smaller. Alright. So if we look at a few more examples, this is just a reminder up top of what all of our components of our function do. And I'll let you refer back to that first slide if you want to know like what does what. Actually, I'll just remind you all. So a vertical stretch. So if A is greater than 1, it's a vertical stretch. If A is less than 1 but greater than 0, it's a compression. And if A is less than 0, which is a negative, it reflects it across the x-axis and it affects the y. Horizontal stretch, if B is actually less than 1 and greater than 0, so if B is a fraction, it does the opposite. Remember, if it's inside the absolute value symbol, it's not as intuitive. The compression is if B is greater than 1, and then the reflection across the y-axis is if B is less than 0 or negative. The horizontal shift, left or right, alright, inside the absolute value symbol is the opposite. So left is going to be a plus h, and right would be a minus h, and it affects the x values. And the shift up is going to be a plus k, and the shift down is going to be a minus k. So if we're describing some transformations here, looking at this first example, this is a k, and it's a minus k, and this is a plus h. So I know that my vertex is going to be moved, and it'll shift the entire graph to the left 4 and up 6, which means that my new vertex is a negative 4, down 6, not up. So this is down 6. So minus 6, which means that my new range is going to be bracket negative 6 to a positive infinity. If we look at example B, this is A, this is H, this is K, and then this negative in the front, we know that it flips across the x-axis, which means that my range is going to be going down. So I can go ahead and put that my range is going to be going to a negative infinity for my range. I don't know about the other side just yet. And my domain is still going to be all real numbers. My A, which is a 3, since A is greater than 0, is going to be a vertical stretch by 3. And when I say 3, that's a factor of 3. When I look at H, since I'm subtracting H, we already talked about this, minus H means that I'm going to go down. I'm going to go to the right 7, because if it's inside the absolute value symbol, if we're in function notation, the parentheses, it does the opposite of what we think. And then the last thing is at K, and since it is plus 1, we're going to go up 1 based on k, which means that our vertex will move from 0, 0 to 7, 1, and then our range is from 1 to a negative infinity, because our graph is flipped. So if we graphed it, it would look like this, be upside down, but actually a little bit over from the vertex, 7 to the right, from the origin. I'm going to come back to C in just a minute. Let's look at D real quick. D has all of our components again. So I have A, I have B, I have H, and I have K. So my A is 1/3, and since A is less than 1 and greater than 0, it is going to be a vertical compression by a factor of 1/3, or you're going to compress it by 1/3. B, switch colors just to make it a little bit easier. Remember, it does the opposite of what we think. And one thing that we'll also do is multiply your B times your A, and it'll actually tell you your movements of your slope. However, you need to keep your negatives and your positives independent of one another. I don't have an example in this video because we kind of kept it separate, but just something to keep in mind, that your B and your A will be multiplied times each other. Since this is a 2, remember, it is the opposite of what we think. You would think that the 2 would make it stretch, but in all actuality, it is a horizontal compression by a factor of 2. Going on to my H. The H is +1, so my H means that we go to the left 1, and that's going to move our vertex. And then the -3 for K means that we go down 3 for our vertex. So the new vertex would be -1, -3, and then our range, because we moved our graph down, is going to be a -3, infinity. I didn't flip it, so it's still going to open up. Now here at C is where you're going to run into some trickiness. If you notice how it's formatted up top, you have a parentheses, B, parentheses, and an X minus H. Here they're all kind of put together. If you first look at this, you're going to think to yourself, okay, yeah, this is moving to the left by 2, and then there's a horizontal compression by a factor of 3. However, that is not the case. You actually need to be able to separate your B from, in this case, C, so that you can actually get the accurate vertex to be able to graph it. So what I'm going to do is actually take out the GCF, which in this case will be 3, because I'm trying to get rid of that 3 with my variable. So this will be f of x is equal to absolute value of 3, x minus 2 over 3. Now I have a true B and a true H that I can use to graph. So I know that my vertex moved to the right 2 over 3, and then the B means that I have a horizontal compression by 3. So my new vertex is going to be 2 over 3, 0, and since I only moved it to the left and right, I didn't actually change my range, so my range is still going to be 0, infinity. So this is something to be careful of. If it's not separated with parentheses, it's not intuitive as to what your transformations are going to look like. And then we'll do one more example and stop it there for this part of the notes, and then I'll pick it back up here in a little bit. So we have the parent function. This is function notation. So what this is saying is that function f is equal to absolute value of x. So it's declaring it for you, like, hey, look, this equals this, which means that we no longer actually have to write f of x equals absolute value of x. If we reference function f using its name, f, then we know that we're moving our function based on absolute value of x, which means that anything in parentheses is essentially you're going to apply the absolute value symbol to it, and then everything outside of parentheses won't have the absolute value symbol on it. So in this particular case, if we rewrote this, we would say f of x, I'm actually going to name this one g of x, is equal to absolute value of x plus 2 minus 3. And we know that this is h and this is k, so this is moving our entire graph to the left 2, and then moving it down 3, which means that our vertex is now a -2 and a -3. So if I plot my vertex at a -2 and then down to a -3, all I did was just shift my graph. So it's still going to go up by 1 and to the right by 1 to the right of my vertex, since I didn't flip it, and then it's going to go up and to the left by 1 to the left of my vertex. And if we use a straight edge, it'll look like this. I actually think I did a better job without using a straight edge, so I'll keep that in mind for future videos. So if our vertex is -2, -3, our domain is still the same, which is -infinity to +infinity, and our range now is going to change because I moved my graph down. So my range is now a -3, infinity. So I'm going to do a few more examples in just a bit. What I'll probably do is just do them in the same video and then combine the two of them. But this is the intro to absolute value functions and then the transformation of absolute value functions.